All right, friends, welcome back. In this video, I'd like to go ahead and start Chapter 7. And you'll notice here by taking a look at the screen that we only have 2 sections here that we're going to cover in Chapter 7. And we're going to go ahead and do a quick quiz over this chapter along with your Chapter 6. So let's go ahead and get into Section 7.1, which is going to talk about matrices and how they apply to systems of equations. Okay, so first, this is not the first time we've seen a matrix, because we did use this concept of matrices in Chapter 6 to be able to do a couple of the things that we did there, but now let's go ahead and formally define what a matrix is. So all it is basically just an array or an arrangement of numbers in a rectangular fashion, okay? And so this would be an example of a matrix in general, where you see that the naming convention that they choose to go with is they basically just call the entries A, but they've gone ahead and used a little bit of a subscript here to tell you what row that entry is in, followed by what column that entry is in. So here you see 1, 1. That is the entry that is in the first row and also in the first column. So here is the first row right here, and here is the first column of all of this data arranged, and so this entry is, of course, where those two intersect there. And so that's why we stick with that naming convention, okay? Now, what we can do here is we can start to define what a matrix is. We can also start to define some of the ways that we can measure a matrix, right? And so we talk about the order of a matrix just being how many rows and how many columns it has. Typically, that is the order that you'll see these dimensions written in. So it does go the number of rows, m, by the number of columns. You'll typically see that written as m by n, or maybe like a 2 by 3 matrix or 3 by 4, etc., etc. If the number of columns matches the number of rows, then of course we have a rectangular arrangement that would mimic more of a square shape, and so we do call that a square matrix for that reason, okay? And so going through here, example 1, it just says simply determine the order of each matrix. Again, what we're going to do here is we're going to write m by n using that little cross symbol in between, and then remember the order goes, it's the number of rows first, and then after that the number of columns. So matrix A there, you can see it's not so important what the actual entries are, but you'll notice that we can have negative numbers, we could have 0, we can have fractions, we basically could have any numeric value as an entry in a matrix. But right here we're asked to write down the order of it. And so it looks like in matrix A, I have 2 rows, and then I have 3 columns. So that would be an example of a 2 by 3. In matrix B, I have 3 rows, and I have 2 columns. So that would be the reverse of a 2 by 3. So that is a 3 by 2. In matrix C, I have a 2 row by 2 column matrix, so this would be the first square matrix example that we'll look at here. And then finally for matrix D, that is a matrix with 1 row and it looks like 4 columns, okay? And so that very simply is how to go ahead and write down the order of a matrix. Now, matrices apply to a lot of really good real-world applications. So what they're best used for is to be able to represent data, right? So you can actually take a whole bunch of different data points from a bunch of different members of your population and then model that information in a matrix, and we can use economics and computer science and all these different other tools at our disposal to be able to make sense of that data, okay? The way that we're going to look at matrices here in college algebra is we're going to look at matrices as they apply to systems of equations, which was the main topic from Chapter 6. And so this is an idea that we saw back in Chapter 6, but it's something that we're going to kind of formally point out now, right? So if you have a linear system like this one right here, what we're going to do is we're going to borrow all of the coefficients of this of these 2 equations, and we're going to go ahead and use those numbers and put them down in what we call an augmented matrix. Augmented in this case basically just meaning that it came from a linear system. And another thing you'll notice here is that where the equal signs were, you'll notice that in our augmented matrix down here, we basically just put a little bit of a vertical line. That is not absolutely necessary, but that does kind of help us to remember that this came from a linear system. And so that line will always go where the equal signs went from our system. So example 2 here, just a really straightforward one. Here is a multivariable linear system, is what we talked about in section 6.3, and we also got some practice doing exactly what we're doing here, which is to take that linear system and to write the augmented matrix that goes along with it. So again, I'm just going through, I'm just taking a look at all the different coefficients and each constant that I've got here, Anytime I have a blank, that would simply just be 0. And so anytime we've got that, we'll write that in. And remember that if it's just the single variable there, remember that there are coefficients of 1 in front of those variables here. And so that is how we're going to go ahead and make sense of those. In the following ones here, we are going to go ahead and see here that we do have a couple of blanks here as well. So we'll say 0y there. And then, of course, we've got the negative in front of z there, so we're going to go ahead and say -1 whenever we write that corresponding entry there. But, again, this is basically a way to represent the linear system without having to write down all the variables and the equal sign. So we could just stick with it straightly as an augmented matrix in this way. And also, one of the things that I forgot there is my little vertical line where my equal signs went in my linear system there, so we'll go ahead and write that in. One of the things that we're able to do with matrices, and one of the more powerful things that it allows us to do, is to be able to work with data, but the way that we're going to do that is by doing some row operations here. And so the row operations that we're specifically going to do with our matrices here are going to be these three. So one of the things we can do is we can swap two rows. So, we can take the first row and the third row and swap them, for example. That'll be the first step that we do down here. You can see that in my original matrix, I didn't change any of my numbers just yet. I just literally took what was row 1, I put it down there in row 3, and then I put row 3 and put it up into row 1. So you could swap rows. Another thing you could do is you could multiply each of the entries of a row by some sort of non-zero constant. We'll see that here as well. That could be a positive number, a negative number. That could be a fraction, we'll see in some cases. And then the third thing is that we can add rows together. Okay, so we can take a multiple of a row and then add it to another row, or we could just straight up add two rows together, and whatever the corresponding results would be, that's something that we can go ahead and replace one of the rows with. So down here it says, in this example, we're going to go ahead and swap rows numbers 1 and 3 first. I've already gone ahead and done this just for the sake of time. So you can see there that I just went ahead and I swapped row 1 with row 3 to get my next matrix in the step-by-step here. And then you'll notice that I stuck with some other conventions here as well. I'm basically telling you what I'm doing as I go from one matrix to the next by going ahead and writing the note in between there. So you'll see that as we go throughout a lot of the different examples today, that there's some new notation there, right? So R sub 1 represents the first row, R sub 2 represents the third row, of course, and you see that little double arrowhead in between them. That just means that I swapped them. Moving right along here, the next matrix that we get is by doing step 2 up there. It says add -2 times row 1 to row 2. So here all I'm doing is I'm taking -2 times each of the entries of row 1, and whatever the resulting entry I get from that is, I'm going to add that to row 2. So just as an example, if I go to this matrix here, in every single entry in row 1, I'm going to multiply it times -2 first. So if you were to do that for this first entry here, of course, that would be 1 times -2. And of course, the result there would simply be -2 there, right? So -2. After that, I'm adding that to the corresponding entry in row 2. So if I were to take -2 plus 2, then of course I would get the corresponding entry in the second row down here, which is 0, okay? And you do notice that I am taking the result of that and I'm replacing the entries in row 2 with that result, okay? So basically, the language that it says is basically do this to row 2. And so that's why we're going to get a new row 2 after doing that to it. Okay, and then step 3, it does say to multiply row 3 by -1/4. That's pretty straightforward. We're just going to take each of the entries in row 3, we're going to multiply them all by -1/4, and then whatever the result is, we're going to go ahead and write that as the new entry there. Okay, so as we go throughout the video here, the notes, we're going to see that as we go from matrix to matrix, we are going to tell you how we jumped from one to the next. So I would very highly encourage you to pause the screen and make sure that you're able to make sense out of the operations that we're doing with our rows. Here in this next example, right? So here you can see that we were doing a lot of different operations between rows, and again, just to save time in the video, I've gone ahead and written this out ahead of time here, but it just says to perform the sequence of row operations on the matrix. So we're starting with the one obviously in the top left-hand corner, and we arrive down to the one that's in the bottom right-hand corner after doing everything that it says to do in between there. So I would very highly encourage you to go ahead and pause the video and make sure that you go line by line here and make sure that you understand where we're getting each new row from. One of the things that we discussed in Chapter 6 that we're able to do with a matrix as it applies to a linear system is we're able to write it in what's called row echelon form, okay? And so while we just kind of let the calculator do it in Chapter 6, I would like to go ahead and show you how that is done here in this video. But let's go ahead and formally define what row echelon form is, right? So when you take a look at a matrix, the way to determine if it's in row echelon form or not is basically if it matches this description right here, right? So it says here any row of all zeros is on the bottom. So the very bottom row will be all zeros if that applies. Not all row echelon matrices have a bottom row of all zeros, but if it does have any row of all zeros, then it will be at the bottom. Secondly, it says for all other rows, the first non-zero entry is a 1. Okay, so if we take a look at this example down here, you'll notice that as I read these rows from left to right, the first non-zero entry is going to be a 1 in every single one of these rows. So the first entry in this row, of course, is 0, but the first non-zero entry is going to be a 1, so that checks out. I have a couple of zeros to start us off here in the third row, but the first non-zero entry, of course, is going to be that 1 in the third row there. So that checks out as well. And then finally it says the leading 1 in a higher row is farther left than the leading 1 in the row that's right below it, or the lower rows. And so that's basically there to say that what you have here in echelon form, or row echelon form, maybe I should say, is you've got this diagonal of 1s going on. Basically, that's what you need to be on the lookout for whenever you are looking at a matrix that is in row echelon form, is a diagonal of 1s, and then everything down below that diagonal here, these will just all be zeros, and then you may have some other numbers here that are above that diagonal, but that is going to be the case, right? And so what we saw in Chapter 6 is that we can take these row echelon matrices and interpret them into the language of a system of linear equations that involve multiple variables, right? So we might interpret this as like 1x plus 2y minus 1z is equal to 4, 1y plus 0z is equal to 3, and then 1z is equal to negative 2. That's how we might interpret that in the language of the augmented matrix in that way. But that's what we're going to have for row echelon form. Reduced row echelon form is even more important, and this is what we let the calculator do in Chapter 6, right? So basically, to be reduced row echelon form, you have all the conditions for row echelon form, but also this additional condition right here that says every leading 1 has zeros above and below it. This was the one that we were more interested in because this was the one that allowed us to say that x was equal to 2, y was equal to negative 4, and z was equal to 8. So basically, if you can take your matrix and write it in row echelon form, or sorry, reduced row echelon form, then that's basically you solving the multivariable system that goes along with that matrix. And so that's why it's so very important for our needs. And so here in example 4, what we want to be able to do is basically just point out row echelon form and reduced row echelon form when we see it. So I want to take you through a couple of these examples here, right? So what you'll notice in this first matrix is that I do have my diagonal of 1s. That's really important. I have zeros all below that diagonal here, and then above it are basically just a bunch of other entries here that may or may not be 0, okay? And so this is a classic example of what we call row echelon form, which we just abbreviate and just say simply REF for short. If we look at the next example here, it looks like here we have a row of all zeros in the bottom, and then we have some 1s there as the first term in each of those rows that is a non-zero entry, and then everything that is above that diagonal, of course, is a non-zero there. So this would be another example of row echelon form. Moving right along here, if we take a look at this matrix here, we notice that the first non-zero entry of the first row, of course, is a 3, and the first non-zero entry of the last row is a negative 1. And so, unfortunately, this does not match either of our cases here, so this would be neither row echelon nor reduced row echelon form for this matrix. And then finally, if you take a look at this example here, it does say that the first non-zero entries of these rows are just simply 1. It looks like that last row is just all zeros there, and then everything above and below these 1s is a 0 itself. So this would actually be an example of reduced row echelon form for that matrix there. Okay, so be very important to be able to look at a matrix and be able to tell what form it's in. Now, again, the reason that we're talking about matrices is because they can model those multivariable linear systems that we talked about in Chapter 6. And so what I want to do here really quickly is I just want to go ahead and demonstrate for you why it is so very useful for our needs by actually applying it to a multivariable linear system here. So Gaussian elimination is something that we talked about in Chapter 6, something that we pointed out at least. But that's what I want to go ahead and demonstrate here for you as we take a look at this matrix, right? So this is an augmented matrix. The first thing I'll do is I'll just go ahead and write the system that this models, right? And so remember that is just simply going to be 1x plus 2y minus 2z is equal to -1. Remember that this vertical line right here corresponds to your equal signs in your linear system. So that's just me doing the first row. And then anywhere there's a 0, that's going to be a term I'm actually not going to write because the coefficient would be 0, and 0 times a variable would just be 0. It's not necessary, right? But continuing there, I'm going to have my 1y, or just y, plus my 1z, or just z, is equal to 9. And then finally, I've got my 1z is equal to -3. Okay, and so this would be my multivariable linear system that goes along with the augmented matrix that I was given, and what we would like to do is be able to go ahead and solve this just like we talked about in Chapter 6. This is really easy to do because they gave you your value for z. All we're going to do here is we're just going to plug that value for z into the second equation and then solve for y, and then once we have that, we're going to take that value for z and our new value for y, we're going to plug it into our first equation and then solve for x, and then we'll be all finished up. Okay, so let's go ahead and take that second equation, the one in the second row, y plus z is equal to 9. I'm just going to plug in my z real quick, so that'll be y minus 3 is equal to 9, in which case we can pretty plainly see that y is going to be equal to 12 in that case. After that, I'm going to go ahead and take the equation in my first row. That was my x plus 2y minus z, or sorry, 2z is equal to -1. I'm going to plug in my values that I know. I know z, and I now know y, and so I can go ahead and take this and use this to solve for x. So 2 times 12 minus 2 times -3, and that is equal to -1. So here x is going to be added to 24 plus 6, and of course that's going to make 30, so x plus 30 is equal to -1, and then we can pretty plainly see here that x would simply just be equal to -31 in this case, okay? And so once all three of your variables are present and accounted for, we could go ahead and write our answer as what we call an ordered triple. Okay, it's very similar to an ordered pair, a point that you might plot in the xy plane. An ordered triple would be a point that we could plot in 3 dimensions. Okay, and so basically the way to write that would be to just go ahead and write it just like an ordered pair, but with 3 entries as opposed to 2. And that is the way that I would like you to go ahead and get used to leaving your answers whenever we are solving a multivariable linear system that came from an augmented matrix in this way. Now, you'll notice that throughout the rest of the video here, I am going to go ahead and show you the work because what we are going to ask that you do is pick up the skill of being able to take any matrix and rewrite it in its reduced row echelon form. I will not lie to you, that is basically like a mathematics puzzle. You're going to be taking something that starts like this green matrix right here, You're going to have to rewrite it using your row operations to get it to look like reduced row echelon form, which we talked about a couple of slides ago. And again, that is like a puzzle aspect. It's kind of like solving a Sudoku puzzle in some ways to figure out how you take your original matrix and use your row operations to get your row echelon form. I will tell you that it's not immediately obvious how to do that. So for our purposes, I am going to show you all the work for being able to do that in each one of the slides coming up here. But I am going to also allow you to go ahead and just type it into the calculator using the same method that we discussed in your 6.3 video. So I have a quick screenshot of that right here, just so I could be able to check the calculator to make sure that I got it right. What that means for you guys is that you are going to need a TI-84 to be able to do questions like these. If you don't have access to one of those, then there are other calculators online for being able to take a matrix and rewrite it in its reduced row echelon form. I'll leave a link in today's Schoology folder for that if you want access to that. But here would be another example of taking a matrix and showing all of the work, just doing the basic row operations here, and rewriting it in its reduced row echelon form in this way. Okay, the homework is going to ask you to do it, and I would encourage you to go ahead and give this a shot if you would like. Again, it's not immediately obvious, but what you're basically looking for, folks, again, in your reduced row echelon form is you want everything to the left of that vertical line in your matrix to look like this. You want that diagonal of 1s, and then above and below each one of those 1s in each one of your rows, you want 0s, okay? So again, it's a little bit of a puzzle to figure that out. I'll let you go ahead and read here step by step to go ahead and do that. But again, for those of you with the TI-84, I will allow you to go ahead and simply just use the TI-84 to go ahead and find your row reduced echelon form in this way. Okay, just a little bit of review about how to navigate to use the TI-83 Plus or the TI-84. Keep in mind you have that matrix menu. So if I pull up my calculator here real quickly, again, that is going to second, and then the button right below the math button, that's your x to the -1 button. You'll see that it says matrix right below, above that button here. The first tab here is the names of all the matrices that you could type in. The next tab over, this is all the math that you're able to do with matrices. Keep in mind that what we talked about in your section 6.3 video is that if I press the up arrow button, it'll immediately take you to the end of the list, and then if you just keep doing the up button, here is your reduced echelon form operation, and here is your row reduced echelon form operation there. And then in order to actually type in a matrix, you can go ahead and go to this third tab over, which says edit, of course. You could pick which matrix you want to go ahead and edit, like maybe I press enter and edit matrix number 1. The default here is to just go ahead and do a 1x1, but you'll notice that the cursor is there on the dimensions for you to be able to type in a matrix of any size or dimension that you like. As we kind of go through here, let's maybe go ahead and practice typing this one in. So it has 2 columns, sorry, not 2 columns, it has 2 rows and 3 columns. So I can go ahead and type that in, 2x3. To get from entry to entry here in this matrix screen, you'll want to go ahead and press enter as opposed to pressing your arrow buttons to try to navigate from entry to entry here. So I now have this set up, ready for me to go ahead and plug in some numbers here. So after I figure out my augmented matrix, I'm just going to go ahead and type in each entry, okay? So again, be pressing enter after you type each entry to automatically push you to the next entry in the list. So we have 2, 6, 16. So I'm just pressing enter after each one of those to lock it in. And then finally we have 2, 3, and 7. So 2, enter, 3, enter, 7, enter. And then that locks it in. All right. So once you have this ready to go, what we need to now do is go ahead and quit out of this matrix. We can go ahead and do that by pressing second mode, which is always how you quit out of anything in the TI-84. And then finally, if you want your row reduced echelon form, then you can go ahead and do the operations if you like on your paper, doing your row operations. But if you wanted to go ahead and do it here strictly in the TI-84, you would simply just have to go ahead and go back to your matrix menu, go to your math tab, arrow up, and then we just want this item in the list right here, the one that says RREF for row reduced echelon form, and then press enter to pull it up. And now what we need to do is go back into your matrix menu and then go ahead and press enter on the matrix A in my list under the names tab. And you'll see here that it actually puts the dimensions of that matrix next to the name, and that is just the calculator's way of telling you that that is a matrix that you've already typed in so that we can keep track of what we've already done. So once you have that ready to go, you just press enter at this point after pulling it up, and it'll automatically put it into row reduced echelon form for you, which is pretty darn handy for being able to actually solve the system here. So we know that, again, this was, oops, I need to switch back to my pen. That was 1x is equal to -1, and then 1y is equal to +3. So 1x is equal to -1, and then 1y is equal to +3. That's how we would interpret that, of course. We could go ahead and do bigger matrices. I'm not going to take you to the calculator to do this one, but I have written it out. So again, writing the augmented matrix, putting a 0 for any entry that we see is missing in the multivariable linear system, and then you're just using the calculator to get our row reduced echelon form here. You'll notice that because I have 1, 2, 3, 4, 5 columns, the 5th column is going to be the one that comes after the equal sign. So that means that I'm going to have an ordered quadruple as my final answer. So this would be a point that you could plot in 4 dimensions, actually. Example number 8 here, this will be the last example that we talk about here in this video, and this actually presents a situation that I do want to go ahead and discuss here, right? So we have our multivariable linear system there as our green matrix. You notice that I've already written the augmented matrix there, and I've already gone ahead and put this into the calculator to get my row reduced echelon form in that next matrix there, and you'll notice what happened here, right? So this is an example of a linear system that I'm not able to write fully in the language of reduced row echelon form. The best I could do is just getting it to this place, and you'll notice that that translates to this multivariable linear system that we can go ahead and continue to solve here. What I want you to notice is that when we translate that back to being a linear system, one of the things that is true here is that you have two equations that both involve this variable z. And so what that means is you can go ahead and represent x and y as expressions involving z. And so that's what I've done beginning up here. So one of the things I've done here is I just said let z be this value a, and I use that value a to just represent that this could be any value in the world. And what that is going to allow me to do is to take my two remaining equations, plug in a for z, and then solve for the variable remaining. So x here is equal to 2 minus 5a, and y here is equal to negative 1 plus 3a. And that gives me the ability to write this as my ordered triple, where the interpretation is that, again, a is any value in the world, and if I were to go ahead and plug in any number I want in here for a, I would end up with an ordered triple that would actually be a solution to the very original multivariable linear system that I began with, okay? And so that's going to pop up from time to time. So if you ever do row-reduced echelon form and it gives you something weird like that, like something that does not look like your diagonal of ones and then zeros above and below, then that means you're going to have to do this little bit of extra work to go ahead and interpret your answer as an ordered triple of infinitely many forms here. Okay, and again, you can be using that in the calculator to type that in as well. So I hope this video has kind of shed some more light on the world of matrices. Again, these are very, very practical things in the real world. It's also something that's going to show up on the ACT if you plan on taking that or retaking that anytime soon. So just trying to give you guys tools to be able to kind of make some more sense out of these very, very important mathematical tools here. But thank you very much for your attention. That's all I have for this video, and I will speak to you guys in the next one.